All right, let's go over exponent law before we go into 4.2, the integral exponents. All right, so number one, product of powers. So when you're multiplying two powers with the common base, in this case base is 2, then we just need to add the exponent. So 3 plus 4, which is 7. Same thing for the next example here. Base is 3 over 4, and they have a common base. So we can keep the base and just add the exponent. 5 plus 7, which is 7. Oh, 5 plus 2, which is 7. So general rule of product of powers is, with the common base is that let A be the base, and X is an exponent. We have to have a common base A, and let's say now exponent is Y. Then when you're multiplying two powers with the common base, we can actually just keep the base and you add the exponent. Next one, quotient of powers. This time, we also need to take a look at the base here, and they have the same base, so we can actually just carry that over and say base is -6. And when you're dividing the two powers with a common base, we just need to subtract the exponents. So 8 minus 5, which is 3. Same thing for the next one. Common base is 7. So we just subtract the exponents, 9 minus 7, which is 2. So general rule of this is that if we have two powers with a common base and we're dividing those two, then we just keep the common base and we subtract the exponents. Number 3, power of power. So this time we have power here, and that power is actually the base of a new power. Okay, so in this case, we need to multiply the exponents together. So you keep the base as 2, you multiply the exponents, which ends up being 2 to the power of 15. Same thing for the next one. We have to keep the base, -3, -3, and then we're going to multiply the exponents, 2 times 4. So we get -3 to the power of 8. So general rule is that if we have a power, a to the power of x, and the exponent on that power is y, then we can say it is a to the power of x times y. Okay, so you multiply when it's a power of a power. Number 4, power of a product. So this time we have a product as a base. In that case, we have to keep this exponent, we distribute it to every single variable and coefficients. If we rewrite it, this is going to be, there's 1, the coefficient here. We have the first variable a and second variable b. So we can say it's 4 to the power of 4 times a to the power of 3 to the power of 4, which is you multiply because that's a power of a power, times b to the power of 2 times 4. So when you simplify, I'm not going to evaluate it, but if you simplify the expression, then it's going to be 4 to the power of 4 times a to the power of 12 times b to the power of 8. So general rule is that if we have a product base, like a times b, and the exponent is x, then we can say this is equivalent to a to the power of x times b to the power of x. And if we have, more variables, for example, a, b, c to the power of x, then we can also say it's a to the x times b to the x times c to the x. Number 5, power of a quotient. This time we have a quotient as a base of a power. So power of a quotient works the same way as a power of product. But in this case, we will have to distribute it to the numerator and denominator. So we have 2 to the power of 3 on the numerator times 8 to the power of 6 to the power of 3, so 18. And then we have that fraction bar there, and then we have 3 to the power of 3 times b to the power of 4 times 3, which is 12. So in general, if we have a quotient as a base of a power, then we can just rewrite it as a to the power of x over b to the power of x. All right, lastly, 2 to the power of 0 is 1. Anything to the power of 0 is always 1. A to the power of 0 equals 1. The reason why this is true is 2 to the power of 2 is 4. And let's say we want to divide that by 2. Then we get 2. And we're going to divide 2 to the power of 2 by 2. Then we get 2 to the power of 1. Let's try dividing the 2 once more. Then you get 1. But notice that our exponent on this side will go down by 1. So 1 minus 1 is 0. So we have 2 to the power of 0 equals 1. We divide by 2. All right, on the next page, let's go over the example. Simplify each of the following expressions. Okay, so we have this complicated looking product, and we're trying to multiply those two. First thing I want to do is collect the like terms. Okay, so let me zoom in here for a bit. All right, so we have number here and here. That's a coefficient. But we also have variable a. And then let's say a squared together, and there's a here. We also have b to the power of 5, b to the power of 6. So when you're multiplying, you can just multiply the like terms together. You can just rewrite it as 7 times negative 3 times a squared times a times b to the power of 5 times b to the power of 6. And I just listed it in order, so I can just combine these two together and these two together. Okay, so 7 times negative 3 is negative 21. A squared times a is a to the power of 3, because you're adding the exponent. Times a to the power of 1 equals a to the power of 3. And for b, same thing. B to the power of 5 times b to the power of 6 is equivalent to saying b to the power of 5 plus 6, which is 11. We have this. So a is negative 21, a to the power of 3 times b to the power of 11. And I would like you guys to try the rest of the example here, B, C, and D, on your own. All right, moving on to chapter 4.2, integral exponents. Let's go over negative exponents. So previously we only talked about nice positive numbers, but now we need to look at a negative number. So this value is an integer value, and that is why it's called integral exponent. So what's so special about this one? The negative in the exponent actually flips the power. It reciprocates the power. Okay, so that just means you flip it over. Numerator becomes denominator and denominator becomes numerator. For second example here, we can just reciprocate the base on its own and to keep the exponent positive. You can just flip it. Flip the number here and switch the sign to positive. This is true because base 3 is actually technically 3 over 1 to the power of negative 5. So if we were to get rid of the negative in the exponent, then you can kind of see that these two flip. So we get 1 over 3 all to the power of positive 5. But from a quotient rule, we talked about how we could distribute the power into the numerator and the denominator. So we can get 1 to the power of 5 over 3 to the power of 5. But 1 to the power of, 5 is just 1. So we just write it as 1 and then keep the denominator as 3 to the power of 5. So this is not different from a rational base. Why is negative exponent reciprocating the base? So let's take a look at another example. If we have 2 to the power of 2, it equals 4. And previously I said let's try dividing it by 2 because the base is 2. Keep it the same. So we know it becomes 2 to the power of 1. That equals to 2. Let's try once more. We get 2 to the power of 0. And what's 2 divided by 2? 1. Okay, there's one more step. We're going to go one more step by dividing it by 2. Then 0 minus 1 is 2 to the power of negative 1. What is 1 divided by 2? 1 over 2. And this is why when you have a negative 1 as an exponent, it just reciprocates it. Let's take a look at example 1. Simplify. Any variables in your final answer should be written with positive exponents. All right, so our key step is to get rid of that negative exponent. So let's start with part A. So we have a rational base with a negative exponent. Let's first use the rule that we learned previously, and we're going to flip over the base to get rid of the negative exponent. So we have 2 over 3 to the power of positive 3. I'll do part B as well. This time we have two powers with different base. We have 2 as a base and the 5 as a base. The exponent rules only works if the powers have a common base. But in this case, we cannot apply it, so we'll just keep it at that. But we can get rid of the negative exponent. This exponent is referring only to 5. So let's rewrite that. So we have 2 to the power of 3 times 1 over 5 to the power of 2. If you want to simplify this a little further, then we could actually distribute that 2 into the base. And so we'll have 2 to the power of 3 times 1 to the power of 2, which is just 1 divided by 5 squared, which is equivalent to saying 2 to the power of 3 over 5 to the power of 2. So I want you guys to work on part C and D on your own. Moving on to example 2. A culture of bacteria contains 5,000 bacterium cells. This particular type of bacteria doubles every 8 hours. If the amount of the bacteria is represented by the letter A and the elapsed time in hours is represented by the letter T, the formula used to find the amount of bacteria as time passes is this. How many bacteria will be in the culture in 8 hours? Okay, so basically they literally gave us the formula. We just need to plug it in. So part A, we can just say T equals 8 hours. So we want to know how much this A, which is the amount, we have in 8 hours. So we can say T equals 8, where A equals, we just plug in the T equal to 8 into the equation, times 2 to the power of 8 divided by 8, which is just 5,000 times 2. Therefore, 10,000 bacteria in 8 hours. Let's double check. The idea is there. They said this particular type of bacteria doubles every 8 hours. So basically, every 8 hours, it doubled. So that is correct. We have confirmed it. And for part B, we can say how many bacteria will be in the culture in 16 hours. T equals 16 hours, then A equals 5,000 times 2 to the power of 16 divided by 8. So 5,000 times 2 to the power of 2. So this is equivalent to 5,000 times 4, which is 20,000 bacteria. And let's double check. They said it doubles every 8 hours. So at 8th hour, we had 10,000 bacteria. And so when it doubles, that was 16th hour. So you can see that 20,000 is a double of 10,000. So that's it for 4.2.